Hello and welcome back to Alakazam Math Made Easy. In this video, we're going to go over limits and how to evaluate them from an algebraic standpoint. In the last video, we talked a little bit about how to evaluate them from a graphical standpoint, but there's an additional level of complexity with solving them algebraically that we'll go into in this video. So if you remember from the last video, you can kind of tell from how we approached the graphical evaluation of a limit that it's the same thing effectively as plugging in the value that you're taking the limit as it approaches into the function, right? Because we're taking, essentially, if we're looking at a graph, we're looking at, or say we're approaching here, we're looking at essentially where the value of that function approaches. And if you remember from probably more of like an algebra kind of class, the value of the function is defined as the y value for a corresponding x. So by kind of starting our evaluation of limits from that graphical perspective, it kind of becomes much clearer that for most cases, it'll just be plugging in the value that x approaches to the function to return that function value. The one little asterisk on this method you have to be careful about is that the function has to be continuous at the value of x that you're looking at for it to work. And if it is, then you can plug in that value. So the example that I have right here, it's a linear function, like essentially y equals mx plus b. That's this function. At no point is any y equals mx plus b function not continuous. So for that reason, we are able to plug in 2 for x, and we get 3 times 2 is 6, plus 4 is 10. So that's what we mean by algebraically. Now, there's a couple common situations that'll come out of this, right? So the first one is the situation we just saw, where we plug in 3, we get 27. That's a number, that's the value of the function at the limit we're taking, right? So at 3, the value of the function is 27. So what happens in a slightly different case, right? So if I plug in 3 to the top, I get 27 again. And if I plug in 3 to the bottom, I get 0. So this case is essentially demonstrating that it's possible to get some number over 0. In any situation where you're going to get a number over 0, you approximate it as infinity, right? So if I were to divide 27 by 1, I'd get 27. If I were to divide 27 by 0.1, I'd get 270. If I were to divide 27 by 0.01, I'd get 2700. So you can see very clearly in this demonstration that as the denominator gets smaller and smaller, keeping the numerator to the same, the value that you get when you simplify it is going to increase. So if I were to say 27 over an infinitely small number, like 0, this number would become infinitely large. So that's the logic behind that. So every time you get any number over 0, you're going to approximate it as infinity. And that's that second case. The third case is I do the same thing. I plug in my 3 up at the top, I get 0. I plug in 3 at the bottom, I get 27. So the second case that I wanted to talk about is, or the third case, sorry, is essentially the opposite of the second case, right? So the second case was some number over 0. The third case is 0 over any other number. And that's kind of much more logical in that it's probably, you've been doing it since you started taking math classes, right? 0, any number divided by 0 is 0. I'm sorry, 0 divided by any number will be 0. Because if I were to multiply 27 times 0, the answer would be 0. So dividing both sides by 27, I would get 0 equals 0 over 27. And you can replace that 27 in that little demonstration with any number, and that'll be the case. So that's the logic behind this. Anytime you get 0 over some number, the limit will equal 0. The fourth case is the complicated one. And this is the one that honestly, a lot of times you'll see on exams and quizzes, because this demonstrates that you actually know how to solve limits algebraically, right? So these other cases are plug and chug. You've been doing that since probably 7th grade. with the slight exception of maybe the second case where you now have to remember that a number over 0 is infinity. But other than that, the process is the same. You've been doing like plug stuff in and populate a number since you've started math probably. So this fourth case gets a little bit more complicated, and I'll explain the logic behind this in a second. So same thing, I'm going to start by plugging into the top and the bottom, and I get 0 over 0, right? What, based on this rule and this rule, what should that value be, right? So I have 0 over some number, right? Which means that I should think it's 0, right? So according to this rule, 0 over any number is 0. But according to this rule, the second rule, I have some number over 0. I have a 0 in the denominator, which should be infinity, right? But also, if you kind of look at it from an algebraic perspective, I have a number over itself, which should be 1, right? So because this special case 0 over 0 is some kind of crazy loophole between 3 traditional rules that we use, it's what we call an indeterminate case. You can't, it's inconclusive. You can't determine an actual numerical value that makes sense based on the way that the function is currently set up. So we're going to take advantage of one pretty common mathematical concept that we've used before, and that's that anytime you multiply anything by 0, it becomes 0. So that's the principle for how we're going to approach this issue, this special case here, and we're going to solve it because it definitely has a limit. We just need to find where it is. So we're going to take advantage of this principle here. So what we're going to end up doing is factoring, right? So again, the problem is that 0 over 0 is in between these 3 cases, right? And we have to figure out how to fish out what the actual limit is. And every time you approach this function, every time you get a 0 over 0 from a limit, follow these 3 steps. The first step is to factor the top and bottom, factor everything out into a linear form, right? So some x plus something, right? Or x minus something, right? So that's what I did here. So I took x squared minus 4 and broke that into x plus 2, x minus 2. And then the denominator is already in a linear form, so I can just go ahead and do x minus 2. So what that allows me to do is I can say, all right, well, because this and this are the same, I can cancel those, right? Because x plus 2 is being multiplied by x minus 2 and also divided by x minus 2 at the same time. So those multiplication and division will cancel each other out, leaving you just with x plus 2. Now, if I try to take the limit at x plus 2, so we've now, okay, sorry, we've factored, that was the first case, and then we simplified, which is the case where we canceled these 2. And then we're going to reevaluate, right? So I'm going to reevaluate the limit at that simplified value, which is x plus 2, and that's going to equal 4. So notice how we no longer get 0 over 0. That's what we want. We no longer want to get that indeterminate form. So again, remember, we factor, we simplify, and then we reevaluate. So there's a couple tricks to make that process easier, because I know it's been a couple years for some people since they've learned how to factor and probably haven't used it in at least a couple months. So at the very least, we'll go over a couple tricks that make factoring easier. So the first little trick that I wanted to go over, if there's only an x minus something anywhere, that usually means that that's what you're going to factor out and cancel, right? So if you remember up here, it was this x minus 2 that got canceled with this x minus 2, right? So it's usually an x minus some number, and like every time that's the case, that number will match up with the one that you're taking the limit at, because remember, that's the case that's becoming 0. And that's why you end up dividing by 0, because that's the value, but also you end up, the numerator is 0, because even though this section here, this x plus 2 is totally valid, you're multiplying it by this 0, which is making that issue. So that's what you want to get rid of. So look for an x minus some number, right? So that's the first thing. And if that's there, and if that number matches the number you're taking the limit at, cancel that, and then you should be good. Another thing that's super helpful, again, we saw it up here, is the case where you have x squared minus a number that is some other number squared, right? So a number that you can take the square root of and get an integer, right? So that'll be 1, 9, 1, 4, 9, 16, 25, those kinds of numbers, where it's like 1 squared, 2 squared, 3 squared. That's what you're going to look for also, right? So that c squared is what you're going to look for. It's that minus c squared. So again, remember, so first red flag should be that we have an x minus something, and that something matches the evaluated thing we're looking at. But also we can break this numerator down into x plus 5, x minus 5. And that's the thing that you should always remember, is if you have an x squared minus some number that's squared, you can always break it up into x plus and minus the square root of c, right? So that's a huge trick that you should always keep up your sleeve, because it ends up taking a lot of the mental, like, oh no, how do I factor this, out of the question, right? And then again, it ends up canceling those two things, and you're left with a valid x plus 5 that you can plug 5 into and get a normal number that's not 0 over 0. There's another example down here. We had a case where there was an x squared minus 9, which 9's square root of 9 is 3. So now I have x plus 3, x minus 3, right? But in this bottom case, this isn't an x minus something, and that something is not the same as this, but it's also not the case that we're looking at. So that we're going to have to factor normally. So there's no real trick for that one. But what I will say is, because we know from here, this first trick, that we want to generally cancel an x minus the thing we're taking the limit at, we can try to divide, we can almost start by assuming that's what we're going to take out, right? So we can assume that we're going to take out an x minus 3 somewhere, because we have x approaching 3. So now it becomes much easier, right? So actually, I think I literally messed this up. So what ends up happening is I can do it from kind of like a more like a division standpoint than a factoring standpoint. So the first step I'm going to do, I know that this is x squared up here at the front. So I know that my x and my x have to be matched, because there's no coefficient in front of that x. If it was 2x, that would be different, but it's just x squared. We also know that we have this negative 12 here and a negative 3 here. So what's negative 12 divided by negative 3? That would be a positive 4. And then we can just verify really quickly that when we FOIL, remember we add let's see, this multiplication and this multiplication, right? So we'll add a negative 3x plus a 4x, and that should equal that number in the middle, and that does. Oh no. Yeah, so that does in that case. So that's just a couple tips on how to FOIL. And then a lot of the times, I just wrote this out for you, just demonstrates that if you can identify the fact that this approaches 2, there's usually going to be an x minus 2 somewhere built into that. That'll be a problem, or some scaled version of that. It could be 2x minus 4, or for this one, it could be, let's see, 3x minus 9, something that'll simplify down to some x minus the thing you're taking the limit at, right? So that's the pattern. Yes, so pattern, the canceled term for the limit as x approaches a will be x minus a. That's what I've said 1,000 times. So why? Again, because that is the thing that's causing that 0 issue. Remember, anything multiplied by 0 is 0. So if you have that term multiplied to a term that would end up being valid, you're going to end up having that 0 over 0 problem, regardless of how many valid things are in there. So by canceling the x minus a terms in the numerator and denominator, you will get rid of the 0 over 0 that's causing your problem. So I hope that really clarified that process. That's a super common limits problem, the ones where it comes out to 0 over 0. So I really hope that this video clarified that for you. If you learned something from this video, feel free to like it, subscribe to my channel. I'm going to be posting a lot more calculus videos and growing the channel as much as I can. I really enjoy helping you guys, so if you want to get notifications when I upload new things, press the little bell button to let you know that. But other than that, good luck.